Hello there, Professor Iris Miano, Math 50, and we're on day, day 9 material. This is covering sections 8.5 and 8.6 concerning solving linear inequalities and then other word problems as well. So here we go. Let's go ahead and add some notes and start things off. What color do we want today? We never use these brown colors. Let's go ahead and use dark brown. Why not? Okay, how do we want to define a linear inequality? A linear inequality has the form of A plus BX is either greater than or equal to, less than or equal to C. Okay, so it could have any of these 4 different inequality symbols there. Actually, I don't like the way that my handwriting went with those. Let me try that one more time for you. It can either be greater than or equal to, less than or equal to. Okay, those look a little bit nicer. Great. And which A, B, and C are any real numbers. Okay, so let's go ahead and test what we think is going to be true about this particular inequality right here. 4 minus x is less than or equal to 3. We want to ask ourselves, like, if we have specific values that we think satisfy it, how would we go about testing whether or not they satisfy it? Well, basically you plug it in and you see if the inequality is true upon plugging it in. So take this inequality and instead of an x, put in a 1 in this case. And then ask yourself, is this true? Is 4 minus 1 less than or equal to 3? Well, 4 minus 1 is 3. So is 3 less than or equal to itself? Well, it's certainly equal to itself. So yes, you would say that it does satisfy the inequality. So yes, it does satisfy. Cool. Now, let's check for -7. If we take in 4 and we subtract off a -7, is that going to be less than or equal to 3? Well, you might want to take care of that double negative business, right? Make it actually the addition that it's clearly meaning to emulate here, and call it 4 plus 7 is 11. Is 11 less than or equal to 3? No, it is not. So then we could say, with a red pen, just gonna go nope and say it does not satisfy. No, it does not satisfy. One more time. Plug in 5 for x this time. 4 minus 5, is that less than or equal to 3? Let's see, what's 4 minus 5? Well, that'll be -1. Is -1 less than or equal to 3? Sure enough, it is. So check on that, and then say, yes, it satisfies. Maybe you're really excited about that last one and you put an exclamation point. Whatever you're feeling, okay? Let's talk about the solution set of an inequality, because as you could see, there were 2 values that we chose to test that ended up being within the solution set. One value that we tested was not. It turns out there's actually infinitely many values that could satisfy an inequality. So it is the collection of values that satisfy an inequality. Okay, so next we're going to graph solution sets and write the solution in interval notation for a couple of inequalities. And so the way that I like to do this is recognize that these inequalities are actually written very well. And by that, if you read out loud the way that these are meant to be described, it would read as x is greater than 3, right? With x being first. This one over here for number 2 is x is greater than or equal to -2. Having x first in the formal name of a single inequality is very advantageous in regard to graphing, because you can just put a tick mark at the endpoint at 3 and let the inequality act like an arrow pointing in the direction in which you're moving away from 3, okay? And the fact that there's no equal to, option here, it's going to be a strict inequality, so we would want to emulate that with a parenthesis, whether you're talking about interval notation or the graph. And I know what you're thinking. You might be like, you know what, I have experience where I've used an open dot to indicate an endpoint that's not part of the solution set in which the parenthesis is synonymous. By all means, when you're doing the graph, go ahead and do that. But if you transfer your notation over to the parenthesis, it's nice because that notation also is involved in the interval notation. So go to 3, and the arrow is pointing in this direction, right? So from 3, you're going to move in this direction, all the way off to positive infinity. Whoop, like so. So in writing the interval notation, I'll keep it in this teal color, we're going to take the parenthesis, take the 3, and then comma, go off to positive infinity. And infinity, whether you are representing it in the positive direction, in which you just put an infinity, no plus sign in front of it, or if you're traveling in the opposite direction, this way, so to speak, if you could see my cursor, that's going off to negative infinity. You always cap it off with the interval notation with a parenthesis, because infinity is a concept. It's not an end place that you can go to. So there's no hard edge to it, so that's why a parenthesis is the good notation for accounting for either positive or negative infinity. Okay, so hopefully that kind of makes sense. Let's tackle number 2. Draw a new number line for number 2. -2 is the only tick mark you need to actually label. You could put more on there and label them if you want to, but just put the endpoint and let the inequality symbol point in the direction that you're going. If you're greater than or equal to -2, then you should have a hard bracket. Let me change up the color for fun here. And you should be traveling this way, right? That's what the direction of this inequality is pointing to if you're letting the inequality symbol act as an arrow point. So we're going off to here, again off to positive infinity. And we have a bracket here on the endpoint to indicate that -2 is actually part of the solution set, going off to infinity. So the inequality therefore gets written in interval notation as bracket. Yep, take that same symbol, -2, comma, infinity, in that order. Is it okay to switch the position of the infinity and the -2, or for that matter in number 1, the infinity and the 3? No, it is not. It needs to read correctly from left to right, and you need to start with your lowest endpoint and either go off to infinity, right, if you're gonna do that, or go to another endpoint. And if you're going off to negative infinity, you'll start off with negative infinity with a parenthesis. So it'll be parenthesis, negative infinity, comma, and then whatever your upper bound is in that case. Okay, cool. So I think we covered all of the bases on that one. Moving on to solving linear inequalities. So you know how we have those properties of equality, APO, SPO, MPO, DPO, for addition, subtraction, multiplication, and division properties of equality respectively. But we also have similarly defined properties of inequality. So the only way, or the only one that really needs to be carefully accounted for is the multiplication or division, that for that matter, of a negative factor. We'll get to that in a second. So anyway, let's go ahead and talk about these principles for inequalities. So if you have a really super rudimentary, like the simplest inequality you could ever think of, and generic as well, not knowing the values of A and B other than A is less than B, literally, that's what this says. If you have A is less than B, then you could, oh, let me actually change the color here, something darker so it shows up better. You could add C to both sides, and you would still maintain the less than relationship between both sides of the inequality. That's fine. Furthermore, you could do the subtraction version of this as well. Just make sure you're subtracting off C and not changing the position of the thing, like so. That would be fine. Positive multiplication property. Okay, so if you have this to begin with, you can multiply both sides by c and maintain the less than, okay? Because c is positive, so since c is greater than 0, right? Okay, now if you're multiplying both sides, or yeah, strictly greater than is what you need. Also, I'll put another caveat here. You can divide both sides by c. And if a c is greater than 0, then it can't equal 0. So you're all good with avoiding undefined values. Okay, so that's also true. Now, this is where it gets tricky. If you have c multiplying on both sides of an inequality and c is less than 0 or a negative number, then you have to change the direction of the inequality, and that's when it becomes a greater than situation for this particular scenario. That's supposed to be a c. Okay, so also you can divide both sides by c, but you must, since c is less than 0, change the direction of the inequality. Okay, great. Now let's go ahead and solve some linear inequalities in one variable in order to test out these properties of inequality, make sure we fully understand them, and just get some practice in solving inequalities as well. All right, so starting off here, the thing we'll want to do is always isolate x, and the thing that we'll need to do is divide both sides by 5 in order to do that. So I'm going to go ahead and just write off of the problem itself, divide by 5 in this manner. I'm going to kind of slash them away there, and I'll be left with x on this side, and here I'll be left with 1 and 3, and don't forget it's negative on this side. So just to be clear, I'm not going to change the direction of the inequality here just because there's a negative present. The thing I divided by on both sides was positive, so that means everything with the direction of the inequality is going to be maintained. So my final answer here is going to be x is still less than or equal to -3. And that's that. Number 2, notice that we have variable terms and constant terms on both sides. So that means just like if this was an equation, I get 4 different ways that I can move forward, but I'm going to choose to do my personal conventions, which is to deal with the variable terms first and do it in such a way that I get a positive result. So I'm going to choose to subtract 3x from both sides as my first move. And then I will be getting 4 is greater than or equal to 2x minus 8. I will then add 8 to both sides. And I will get 12 is greater than or equal to 2x. Okay, and then lastly, I'll divide both sides by 2. So, yep. That'll give me 6 is greater than or equal to x. And I know what you might be thinking looking at this final answer. You might be saying, oh, well, you know what? I really like it better when my inequality reads with the x first. No problem. You can do what's known as a pancake flip for this one in order to have it read better from left to right. So pancake flip is, pretend you're putting your spatula underneath the inequality 6 is greater than or equal to x, and flip it over like you would a pancake. Okay, so what was on the left is now on the right, and the direction of the inequality has to switch as well. So the pancake flipped equivalent version of this inequality would therefore be x is less than or equal to 6. Now I didn't change the direction of the inequality because of any multiplication on both sides by a negative factor. I did it so that the inequality reads better, okay? So this one is equivalent to this one over here, which I'm going to present as my final answer. So hopefully everybody's okay with that. We can talk more about it in class if you would like. Let's do one more example of this type, and then we'll move on to something else. Okay, so we want to ultimately isolate this x, yeah? So there's several things being imposed on the x, the most direct being multiplication of 3, then the addition of 1. The least direct thing is the division of 4. So let's multiply both sides by 4 in order to and call it 4 over 1 if you want to. in order to move forward with this solving for x, okay? And I'll go ahead and switch up the colors, which I did not do for a previous problem very well. So that'll just be 4's over here, and we'll just have this entire numerator left behind in the next step. This 4 and this 2 have a common factor of 2. 2 divides itself to once, it divides the 4 twice. Okay, so now we are left with just 3x plus 1 on the left-hand side, and that's less than, looks like that settles down to a 2. We're going to next subtract 1 from both sides, and we'll be left with what? 3x is less than 1, and then divide both sides by 3. We did not have any instance of needing to change the direction of the inequality by virtue of multiplying or dividing by a negative factor. So you're not seeing it, but it definitely could happen. So those will be all canceled. This doesn't reduce any further. So we have a final answer here of x is less than 1/3. Okay, great. That reads nicely. No need to pancake flip on that last one. Oh, look at this. We needed to not only solve each, but graph them and write their solution in interval notation. So I'm getting a little ahead of myself. All I've done with these 3 problems so far is I have solved them. So now it's our job to graph them as well. Quick fix. All right, here's an appropriate graph. Here's the 1 tick mark that I need to label, -3. And where am I going? It looks like the inequality, if it was an arrow point, it'd be pointing, going to the left. And I have the equal to option. So I'm going to go ahead and, in this purple color, draw a bracket and color everything in off to -infinity. -infinity. So the interval notation for this would be starting off from the depths of -infinity. Pretty much you read your graph from left to right, and that tells you the order of the elements. And also, if you transfer over to this bracket and parenthesis notation on your graph itself, it's the same exact encapsulation in the interval notation too. So I think it's very useful in that regard. All right, so that'll be the graph and interval notation for this particular, for number 1. Now for number 2, here's the graph that we need, and we are less than or equal to 6. So from here, again, we'll do a bracket, and we'll go in this direction. Go ahead and do that in pink. And we're going off to -infinity. So the interval notation will therefore be -infinity, parenthesis always on -infinity or +infinity all the way up to 6, and bracket, because we need to have that endpoint be part of the solution. Okay, I'll also box that one up too. Lastly, I know 1/3 is not a very good, tick mark label, but it's fine, just label it. And then we're going off to -infinity yet again, but we're not going to include the endpoint. So let me get a new fresh color on this one. Let's do this green. We're going to have a parenthesis here on the 1/3. And then let's color everything into -infinity. And then the interval notation will be -infinity, comma 1/3, parenthesis on both ends. Okay? Cool. Let me know if you have any questions or want to see any more of those types when we get back together for class. All right, let's talk about solving compound inequalities. Now this will be along the same lines as what was presented beforehand, but we just need to remember one thing. Whatever operations you perform in order to isolate your x variable, you need to perform it on all sides of the inequality. There's 3 different places, right? There's the left-hand side, the right-hand side, and then the middle too. So let's do what we need to do in order to isolate this x right here. And the first thing we'll want to do is add x. Add 1 to both sides, all sides, all 3 sides. It'll eliminate here as desired, and then this on the side will become what? -9 is less than or equal to, now there's just 3x in the middle, and less than or equal to 6. And then let's divide all sides by 3. And we'll slash away some stuff, right? We're going to reduce these to 2 over 1. These cancel out outright, and we're just left with x as desired. That's a 3 there and a 1 there, but remember it's negative on that end. And then, where am I? Here we go. So that'll be -3 is less than or equal to x, which is less than or equal to 2. Said another way, you can say that x is between -3 and 2 inclusive. We're including those endpoints there, okay? Great. Let's graph the solution and write it in interval notation as well. We're not going to skip those steps because I caught myself. I'm going to catch myself this time. So here, because of the nature of this inequality here, oh, sorry, we never wrote down the idea. Let's go back to that a little bit. What's the idea in solving compound inequalities? I said it out loud, but I forgot to write it, so let's go back and do that. The idea is solve as usual for inequalities. But do operations to all sides. I'll put all in all caps, so you really know I mean it. Okay, great. So moving back to what we were doing here with this graphing, we have 2 endpoints. We have -3 and we have 2. If you want to put like a 0 in between, that's fine. It's unnecessary though. The only 2 endpoints you really need to graph are the ones stated in the solution. And we have equal to option here and here, so that means on both of these endpoints we're going to be putting brackets, and then we're going to color everything in between, and that's how you'll graph it. Here we go, successful graphing of the inequality representing all the values between -3 and 2 inclusive, and then the interval notation will therefore be -3, 2, brackets on both ends. Brackets here in the graph, brackets here on interval notation, okay? Great. Let's do one more, and that'll be it for this handout, for this part of the lecture notes, and then we're also going to do 8.6 in the same video. Here we go. Let's go ahead and subtract 2 from all sides to begin the process. That'll give us -20 on this side. Careful, because it's a -18 and then you're subtracting 2, so that'll give you a grand total of -20. There's still a 4x left in the middle, and oh sorry, 30 minus 2 gives me 28. All right, next we're going to divide all sides by 4. And let's cancel out some stuff. That'll give us a 7 over 1, or 7 here. The 4's cancel out, right? And we're left with x in the middle. That's going to be a 5 over 1, or just 5, but it's negative. Okay? So cleaning up house, we're left with -5 is less than x, which is less than or equal to 7. Okay, so something a little bit more special is going on here in this compound inequalities graph. We still have the lower bound and upper bound that we need to plot. Of course, you can put what, 0 in between, maybe a little closer to the -5 if you want to be kind of scaled properly. And then what do we need to do? Well, we need to put appropriate notation between these endpoints and on the edges of the endpoints. Since we don't have the equal to option here on the -5, we're going to put a parenthesis there. And if you're still on the open dot, closed dot, you'd put an open dot on the -5 and a closed dot on the 7. I am choosing to upgrade to this parenthesis bracket notation because it's the same for the interval notation, which I also have to tackle as well. So interval notation will therefore be parenthesis -5, 7, bracket. And that is that. Great. So let's go ahead and just step right into the next next section here on ratio and proportion application problems. My goodness, and there's lots of examples here, so you'll get a lot of demonstration out of this one. Let's add some notes. And we'll start off with this electric blue color. How pretty. Okay, so a ratio is defined as a comparison of two quantities by division. So therefore the ratio of A to B is A over B. It's just that simple as far as defining it this way. Certainly you could also define it with this colon notation, but that's not something we're going to be using very much. What else could we do in defining a proportion? A proportion is, it can be defined different ways depending on the context. Earlier we defined a proportion as being a fraction or a decimal representation of parts of a whole, right? For this context, what we're going to be doing with the next couple of examples, a proportion is going to be equality between two ratios. Oops. Ratios. So then I'm getting ahead of myself because the next thing that I want to say is that proportions also could be attributed to rates. Also works for rates. What is the difference between a ratio and a rate? A ratio is a fraction whose numerator and denominator have the same units. So like 5 inches to 4 inches would be an example of a ratio, or no units at all. Whereas a rate, the numerator and denominator do not have the same type of units, and they have incommensurable units is what one way that you could describe it for rates. Okay, it could be verified using cross multiplication. That's something that we're going to do right away in this first example, and they can also be solved using cross multiplication as well if there is an unknown involved. Okay, great. Handwriting is atrocious. Now let's go ahead and do the first, or the second thing mentioned in this three-part kind of overview of what a proportion is, and verify if the ratios are equal to each other. So we'll do that using a proportion. So really we're just going to take our 5/12 and set it equal to 20/48 and say, well, is this true? Are these two things equal? So the cross product or cross multiplication dictates that you go across the way and multiply these things. So on one side of the equation you would have 20 times 12, and you got to ask yourself, is that equal to 5 times 48? So 20 times 12, I believe, is going to be giving us 240. Yep, 240 on this side. And is that the same as 5 times 48? It is. So this proportion is therefore verified, so that means the ratios are indeed equal. So yes, they are equal, we could say. I'll change up the color scheme for number 2. Let's go this pretty maroony color. There are 16 ladybugs for every 9 spiders. 16 ladybugs, I'll call them LBs for short, for every 9 spiders. Okay, and so there are 4 ladybugs for every 3 spiders in this other scenario. Okay, so we want to ask ourselves, are they equal? So this is what I mean by like this proportion being something that can also work for rates, because in the number 1 scenario, having no units associated with the numbers and the fractions, those are technically rates being set equal to each other. And with number 2, these are technically, or sorry, ratios. Number 1 is ratios, number 2 is rates being set equal to each other. Sorry, I misspoke before. But the process of verifying them is still the same. You're going to take the cross product, okay? Ignoring the units, of course. Just take the numbers in the process of doing the cross multiplication. You'll ask yourself, is 9 times 4 equal to 16 times 3? Well, no, it's not. On this side, you're going to have 36, right? And 16 times 3, if I'm not mistaken, is 48. So these are not equal to each other. So therefore, you would say, no, they're not equal. No, they are not equal. Donezo. Now, then the next style of problem that you would see in which you would use your cross multiplication skills would be if you were given an unknown in the midst of your proportion, and you would use cross multiplication in order to solve for the unknown. So let's go ahead and practice that as well here. Let's do up a different color now for funsies. Let's do this orange, get a real bright autumn vibe to it. All right, so on this side we'll have 8 times 5 right here, and that's equal to 6 times 3x. So that'll be 40 here, 18x on this side. How do you solve this equation? Well, you divide both sides by 18 in order to get that x by itself. This is not going to divide evenly on this side, but that's okay. You can have a final answer that's a fraction. There's no need for it to be not a fraction. So what are we going to do? Well, let's go ahead and see if we could simplify this a little bit. What's the greatest common factor of 18 and 40? Probably it's just 2. Let's take out a factor of 2 and we'll be left with 9 here, 20 there. Are there any more common factors? No. So that means x is going to equal 20/9. And do you need to convert that into a mixed number? No, it's fine. Just make sure it's simplified all the way down. That's all that I would ask. Okay, let's do this one more time, only with this other proportion. Cross product being initialized here, we'll have 3 times 2x on one side of the equation equal to 8 times 9. All right, so that's 6x equals 72. Divide both sides by, let's do this, 6. And what is 72 divided by 6? I believe that's 12, right? I shouldn't say this stuff out loud if I'm not entirely sure. It ends up that I'm right this time. All right, so therefore x equals 12. And we're done there. Cool. So as long as you've got your multiplication, division skills in play, you know, it's relatively breezy. And if not, I mean, you can just retrieve your calculator. That's perfectly fine for this course. All right. So solving proportion problems. So you're going to be given word problems that contain the idea of a proportion. It's your job to be able to set up the proportion based on what you've read and then solve the proportion for an unknown. So here is a 5-step list that you can go through, knock them out one at a time in order to solve your proportion problems. Step 1 is going to be identify the 2 quantities being compared. And then next you'll want to identify the unknown quantity and assign the unknown quantity a variable. Step 3, identify the 2 ratios needed to solve the problem and to create the proportion. And then you'll be able to set the 2 ratios equal. Solve the proportion problem with cross multiplication, and then write the answer in a full sentence, as we need to definitely practice doing pretty much every single time we tackle a problem. All right, here's example 1 of this cache of examples. The scale on a map is 1 inch for every 30 miles. So that's 1 inch. I'm going to go ahead and change the color actually. 1 inch for every 30 miles. Okay, the distance between 2 cities is 420 miles. Okay, noted. So I'm just writing that down. How many inches would this be on a map? How many inches? I don't know. How about X inches? And X inches is supposed to be associated with the 420 miles that was mentioned here. So this is going to be one ratio and another ratio. So have I done those steps properly? I have identified the two quantities being compared. I have identified the unknown, that's the X inches here, and I'll assign it a variable. Okay, and then identify the two ratios and then create a proportion by setting them equal to. So this is step 3 right there. And now I'm going to perform step 4, solving the problem by doing the cross multiplication. Okay, so here we go. Ignoring the units, just multiply the numbers and you'll get what you want. So that's 30 times x on this side, and then 1 times 420, you can just call it 420 on this side. Divide both sides by 30 in order to get x by itself. And I believe we've got 14, if I'm not mistaken. Let's go back here. Oh, actually I want to do some slashing with the pink, because the 30 slash away and I get x by itself. The 0 slash away, and then 3, how many 3's are there in 42? If I'm not mistaken, it's 14. 3 goes into itself once. Okay, so then x equals 14 is going to be my solution, but now I need to go back to the context of the problem and write the final answer in a sentence, which is to say 420 miles is 14 inches on a map. That's how you can bring all of this information together in a way that's conducive to the context, that makes sense according to the original prompt. All right, box it up and call it a day on that one. Great, moving on to the next problem. Let's go through the same series of steps. Suppose a 6-foot tall man, 6 feet, casts a shadow of 3.2 feet. Here's an example of a ratio, right? Because the units match up. Okay, so here's the, and I'll put little notes off to the side just to keep it straight. Here's the man, here's the shadow. At the same time of day, a tree casts an 8-foot shadow, a shadow of 8 feet. So 8 feet shadow. How tall is the tree? Okay, well I can create another ratio over here with an unknown value in feet for this the height of the tree. And that'll answer this question right here. Okay, set it equal to each other because it's supposed to be the same type of day, so there's supposed to be a proportional relationship between anything's height and its shadow. Particularly if we're talking about the same time of day, then the proportion should be, like the ratio should be equal between the two things in regard to their heights versus their shadows. So cross product time. Let's do that, why not? Mix up the color scheme a little bit. Remember, just focus on the numbers and the variable, and we will get this, if I'm not mistaken. What's 48 divided by 3.2? I don't know. Let's reach for our calculators. It's all going to cancel here as desired, and doesn't go in evenly, so necessarily, I'm not sure. Oh, it goes in exactly 15 times. That's cute. All right, but I wouldn't have seen that just from my, division skills offhand. So reaching for the calculator was appropriate here. X equals 15. So go back to the context of the problem. How tall is the tree? The tree is 15 feet tall. And that is that. Okay. Cool. Moving on, I believe we have some, oh no, we have one more of these types of problems, the proportion problems, and then we are going to talk about percentage problems, percent increase and decrease again, which we've already covered. We're just going to revisit this. All right, so for number 3, according to the Statistical Abstract of the United States, in 2001, there were 1.22 fatal airplane accidents per 100,000 flight hours. Wow, okay, that's grim. Also in 2001, there were a total of 321 fatal accidents. How many flight hours were flown in 2001? Okay, so the first rate is going to be the 1.22 over 100,000. Okay, so this is going to be fatal airplane accidents. So we'll call that FAs, fatal accidents, 1.22, and then the 100,000, the units is flight hours. So we'll call that FHs, if you like. Okay. Oh, let me not get ahead of myself here. Oops. Let's erase that. And we have this other ratio that's in play, which is going to be 321 fatal accidents. So they're like, how many flight hours does that attribute to if we indeed are still in proportion, which is the assumption here. So let's go ahead and put an equal sign in between, and we are going to implement that cross product in order to solve for the unknown number of flight hours. So that's 321 times 100,000. So with 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 zeros tacked on. So 32,100,000 on that side, and then I have 1.22x on the other side. Let's divide both sides by 1.22x. 1.22, that is. 1.22. Cross it out here. And reach for your calculator, right? Don't do this by hand. You don't have time for this. 3, 2, 1, and then 5 zeros. 1, 2, 3, 4, 5 after that. Divided by 1.22. All right, wow. That'll be, sorry, let's make the color scheme back to this. X, therefore, equals 26 million. Oh, you know what? And we're going to round to the nearest whole flight hour. Sure. It rounds pretty nicely anyway. 26,311,475.4 is the actual calculation that I get, but we're going to just shave this off because their flight hours in the original problem was, you know, a whole number. So let's have our flight hours in our response be also a whole number, which is easy. We'll just round to the nearest whole number, which is just going to really take off at this 0.4. Okay, so our final answer should read as there were 26,311,475 flight hours flown in 2001. And that's that. Oh, sorry, I didn't put a period at the end of that sentence. There. Now it's complete. All right, so those are our proportion word problems. Let's wrap up this lecture with some percent change problems. And remember, it's the same as it's been defined earlier. Increases, for percent increase problems, you're going to multiply by 1 plus the decimal representation of the percentage. Alternatively, if you experience a percent decrease problem, the multiplier that's appropriate there is 1 minus the decimal representation. Of the percentage. Okay, so we have some guidelines which are nice. It's always nice to have guidance with word problems, and so hopefully this will help you on your way. And we'll definitely keep this in mind as we experience demonstrations of the following examples afterwards. So what are the steps? We want to first identify what the problem wants you to find, so your unknown, and then assign that unknown a variable. Determine if there's a percent increase or decrease. Set up the equation using the appropriate percent change. Solve the equation, interpret the final answer in a complete sentence based in the context of the problem. Cool, let's do it. All right, you just purchased a new computer. In example 1, the price of the computer, including 7.5% sales tax, was $1,343.75. How much did the computer cost before sales tax? Okay, so this price that you paid is including this 7.5% sales tax. So this is a percent increase problem. And therefore, let's let X equal, and whatever, you could do C. How about computer equals C? That'll be the cost of computer before sales tax. Okay, so therefore, we take this $1,343.75, and we say that this is, see how I said the word is and I wrote the equal sign? Okay, that's translation in effect. This price is an increase, so it's going to be, we need the decimal representation of this is 0.075, and since it's an increase, it's 1 plus 0.075. is going to be your multiplier. So that's 1.075 times C. So let's divide both sides by this 1.075. We'll do it in a different color in order to get the original price before the sales tax. Boop, boop, boop. Those are both ones. Reach for your calculator. Don't try and do this by hand. Why would you? 1,343.75 divided by 1.075. And you should get $1,250 exactly. It's like it was meant to be. All right, so therefore C equals 1,250. So again, take this number, put it in context, write your response in a sentence. The cost of the computer before sales tax was $1,250. Just leave it like that. I mean, you could put .00 at the end if you really want to, but since there's no sense to it, it just was a nice round number, you can leave that off, in my opinion. Okay, and I'll go ahead and box up the final answer just to give it some closure. Okay, let's see what we got here. Oh, this is the last problem. And so we'll want to more or less go through the same steps in exactly the same order. Let's just first read through the problem all the way. Suppose you have just learned that a local sporting goods store is having an end of the season sale on ski equipment. I don't know about you, but I don't identify with this problem very much because I don't go skiing. So if that's you, just understand that it's a sale. You can replace ski equipment with whatever it is that you might go to a store to purchase, you know, like clothing or whatever. Not that we do that anymore because of the pandemic. We probably more or less buy things online, but whatever. Sales are sales are sales, and they could happen online too. Anyway, everything has been marked down by 60%. That's quite a sale. The sale price on a pair of black diamond skis, replace that with something that interests you more, is $224. What was the original price? Okay, so this is definitely a percent decrease problem. Anytime you're dealing with sales, right, you're the price of the thing that you're going to it was marked down by 60%. Sale price is this. So that'll be, yeah. So the original price is going to be larger. So the $224 is a decrease from the original price. Yes, so it's a percent decrease. Go ahead and just kind of make a note there. All right. The $224 is 60% decrease. So 60%, go ahead and write that as 0.6 or 0.60 if you want to, but that's the last zero is unnecessary. So since we're a percent decrease, we're 1 minus that, which is 0.4. So that's going to be the multiplier that you put on what? We haven't identified our variable here. Well, what is it? Skis, black diamond skis. Let's go B for original price of black diamond skis, whatever. Cool. It looks like skis is spelled wrong, but it's fine. If I put IES, it'd be skies. Sorry. I'm a terrible speller, so I always am like second guessing me on how it's spelled, but it says skis right there, so I know that it's right. Okay, so this 0.4 is going to be multiplied by a B, which is what we chose in order to represent our unknown, which we've defined here. Cool. Now we know what to do. We need to divide both sides by that 0.4 multiplier, okay? So go ahead and do that in this lighter green for funsies. Just mix it up. Those cancel out. We'll be left with our B, and reach for your calculator, okay? So what is, hold on, 224 divided by 0.4? 560. So therefore B equals 560. So therefore, the original price of the black diamond skis, or you could just say skis if you're just like, I don't feel like writing this whole thing out, but I established this, so I feel like I gotta do it, was $560. And that's all there is to it. Okay, so you're going to have some practice in class with various problems of this ilk in your small groups. I'm always there to help, but I want you guys to get started in your small groups on your own. Okay, and that's it. So I'm going to go ahead and sign off, and I will see you shortly in class.